In this video, we will be discussing how quantum mechanics is able to predict the hydrogen emission and absorption spectra. In particular, we will be looking at how we can use the concept of quantized energy states to be able to determine the frequency and/or wavelength of photons that are either absorbed by hydrogen atoms or emitted when an electron in a hydrogen atom moves between different energy levels. First, though we will be restricting our discussion in this video and the related calculations primarily to the hydrogen atom, it should be noted that quantum mechanics can actually explain the spectra for more than just hydrogen. The reason that we are restricting our discussion to just the hydrogen atom is mathematically it is the simplest one to work with. For the other atoms, because there are interactions between electrons, determining their spectrum is much more complicated. So how does the quantum mechanical model of an atom explain the atomic spectra? Well, each wavelength in the spectrum of an atom corresponds to an electron in that atom transitioning between various orbitals of the atom. When an electron is excited, which means that it is absorbing energy, it transitions from an orbital in a lower energy level to an orbital in a higher energy level. It takes the energy that it absorbs to do that transition. When an electron is said to relax, that is when it transitions from an orbital in a higher energy level to an orbital in a lower energy level. And in that process, a photon of light is released, and the energy of that photon corresponds to the difference in energy between the higher energy level and the lower energy level. This goes with our first law of thermodynamics, which says that energy can't be created or destroyed. So if you have an electron transitioning from a high energy level to a low, more stable energy level, it is reducing in energy, is becoming more stable, and so the extra energy between those two energy levels has to go somewhere. Where it goes is it comes off as a photon of light, and that energy of the photon correlates exactly to the energy difference between the orbitals. There are several terms that we will use when talking about the transition of electrons between various energy levels. There is excitation, which occurs when an electron moves from a lower energy level to a higher energy level, and then there is relaxation, when an electron moves from a higher energy level to a lower. In order for an electron to move from a lower to a higher, if a photon of light is the source of the energy, then the photon is said to be absorbed. The photon comes in, the atom absorbs the photon, and moves the electron from a lower to a higher energy level. Now, in order for that transition to a higher energy state to occur, the electron must gain the correct amount of energy corresponding to the difference in energy between the final and initial states. Electrons in higher energy states are unstable and tend to lose energy and transition to a lower energy state. When an electron transitions from a higher energy state to a lower energy state, it emits a photon. So a photon of light comes off. Because again, the first law of thermodynamics says that energy can't be created or destroyed. If the electron moves to a lower energy state, the atom reduces in energy, and that extra energy, the difference between the two energy states, has to go somewhere. It comes off as a photon of light. Each line in the emission spectrum corresponds to the difference in energy between two different energy states. For example, an electron that transitions or relaxes from the third to the second energy level will emit a particular frequency of light. We could also, if we were in the third energy level, have it relax down to the first energy level, in which case it would release a different photon. This time, because it was moving from a high energy level to an even lower energy level, the 3 to 2 transition would emit a photon with a shorter wavelength or a higher frequency. We can calculate the energy of each one of the energy levels for a hydrogen atom using our Rydberg equation. the energy of a particular level. N is the principal quantum number. Again, N can have values from 1 to infinity that go up in integer values. So 1, 2, 3, 4, 5, up through infinity. So the energy of a particular energy level is equal to the Rydberg constant, which is a particular value for the hydrogen atom, which is negative 2.18 times 10 to the minus 18th joules times 1 over our principal quantum number squared, where that principal quantum number is the value associated with a particular energy level. So if we are in the n equals 1 energy level, which is our ground state, the lowest value that we can have, again because n starts at 1 and counts up. So the lowest energy state, the ground state for hydrogen, is the n equals 1 energy level. To find the energy associated with that level, it would be the energy for the first, so E sub 1, is equal to negative 2.18 times 10 to the minus 18th joules times 1 over 1 squared. The reason for the negative here is because when we're expressing the energy for electrons that are bound to an atom, we are taking that energy as being relative to when we pull the electron completely off. It takes energy to pull the electron completely off, and we set, when the electron is fully removed from the atom, we set that as a 0 energy level. So as the electron comes in, the attractive force between the proton in the center of the nucleus and the negative charge on the electron attract each other. And as they get closer and closer together, you are reducing in the potential energy, which gets translated into energy of photons being released. So as the electron comes closer and closer in, energy is released, and it gets released in the form of photons of light. And the particular wavelength or frequency of that photon is dependent on the energy change between the various energy levels. So it depends on where it starts and where it drops down to, or where it relaxes to, and the energy difference between those two levels dictates what particular wavelength or frequency of light is going to be coming off. Because we are able to calculate the energy of each one of our various energy levels, we can actually use those calculations to predict the wavelength of light in the emission spectrum of hydrogen by calculating the difference in energy between the two states that an electron transitions between. Now, for an electron in an energy state n, any one of the excited states, there are n-1 different energy states that it can move to. The reason for the n-1 is the lowest state we can have is the first energy level. So for example, if you were in the fifth energy state, it could go from 5 to 4, 5 to 3, 5 to 2, and 5 to 1. So that was a total of 4 different transitions that were possible. So you started out in the fifth energy level, and there were 5 minus 1, or 4, different transitions that it was able to do. Because each one of these transitions correlates to a different photon coming off, an electron in an excited state can generate n-1 different lines. Both the Bohr and quantum mechanical models can predict these energy lines very accurately for a one electron system. Because the Bohr model doesn't take into account the interaction between electrons and has, as we described before, some difficulties with it, it is unable to account for multi-electron systems. We can actually account for those using more advanced quantum mechanical models, but those are beyond the scope of a general chemistry class. So we will be restricting our view to just hydrogen atoms. If we want to be able to calculate the energy of a photon, or the wavelength and frequency of a photon, because all three, as we have previously described, are interrelated, what we will need to do is determine the energy of the particular state that the electron starts in and ends up in. The energy of the photon released is equal to the difference in energy between the two energy levels where the electron is jumping between. We can calculate it by subtracting the energy of where it starts out from with where it ends up. So the change in energy for the electron is equal to the energy of the final state minus the energy of the initial state. Because the electron moves down to that final state, and this is the difference in energy between where it started with and where it ended with, and from our understanding of the first law of thermodynamics, which states energy can't be created or destroyed, that energy difference between where it starts and ends has to go somewhere, and that energy is the energy of the photon. So the change in energy of the electron, the difference between the final state and the initial state, is both the change in energy of the electron in the atom, and because we have to account for that energy, this is also the same value of the energy for the photon. This works both for the excitation and the relaxation. So we can look at the energy of a photon that would be required to excite an electron from perhaps the 1 to the 2 energy level, or the 2 to the 3 energy level, or the 2 to the 4, or the 2 to the 5, or the amount of energy of a photon that we get from the relaxation from a higher to a lower energy level. So the values for our N final and N initial, so this would be the final energy state, and an I would be the initial energy state. The difference between those two will give us the energy of the photon either being absorbed or emitted. The sign here, the negative here, accounts for whether the electron is coming in and being absorbed or coming off and being emitted. We will use a negative sign for the energy to denote that the energy went down, so a photon comes off. If we calculate a positive value, that means that a photon came in and was absorbed. So a negative sign on our change in electron energy will indicate that a photon comes off. A positive value will indicate that a photon was absorbed. The actual energy of the photon has to be positive. Photons cannot have negative values. So we will be using the plus or minus sign associated with this equation, or the value for the change in energy of the electron, as being an indication of whether a photon is absorbed or released. Let's now look at an example of how we can use some of this information to do a calculation. So we're going to determine the wavelength of light that is emitted when an electron in a hydrogen atom makes a transition from an orbital in n equals 6 to an orbital in n equals 5. So what we have is we have our higher energy level. This is n equals 6, transitioning down to n equals 5. So the electron starts here, it relaxes, goes down, and so a photon of light should come off. So what this means is that we expect the energy to have a negative value for the transition. So our transition of our electron, the delta E value, should be a negative number, right? Because if it's negative, that means the energy goes down. The negative here indicates that energy was lost, and that lost energy is a photon coming out, right? So this is what we're working with. So that tells us that the N initial is equal to 6, the N final is equal to 5. Now, using our Rydberg equation, the change in energy of the electron is equal to negative 2.18 times 10 to the minus 18th joules times 1 over n final squared minus 1 over n initial squared. We can now plug our values in. Change in energy of the electron is negative 2.18 times 10 to the minus 18th joules. N final is 5, so that's 1 over 5 squared, which will be 1 over 25, minus 1 over our initial value, which was 6, so that would be 6 squared, or 36. So we have essentially 1 over 25 minus 1 over 26. 1 over 25 is a bigger number than 1 over 26. So when we do our calculation here, 1 over 25 is a bigger number than 1 over 36. So 1 over 25 minus 1 over 36 will give us a positive value inside our parentheses. Because we're multiplying that by a negative number, we'll end up with a negative value for our change in the energy of our electron, which is what we predicted at the start. So if we plug our numbers in to a calculator, you'll get our delta E is equal to negative 2.6644, and then that 4 is repeating, times 10 to the negative 20th joules. So this is the change in energy for the electron. Our negative sign here indicates that energy is coming out, right? So that means that the photon is coming off. So energy out, therefore photon released. The energy of the photon is the numerical value, right? The energy for a photon has to be a positive number. So leaving the negative out, the value 2.6644 for repeating times 10 to the negative 20th is the energy of the photon. And from earlier videos, we had that the energy of the photon is hc over lambda. We could also have Planck's constant times the frequency. Depending on whether we're interested in frequency or wavelength, we'll use one of these two equations. In this case, we want wavelength, and so we'll be using this one. If we rearrange this equation here, solving for wavelength, we get our wavelength is equal to Planck's constant times the speed of light divided by the energy of the photon. Plugging our numbers in, Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Times our speed of light, 2.998 times 10 to the 8th meters per second. And we will multiply this by 1 over our energy, which is the same thing as dividing by our energy. So our energy for the photon was 2.6644 repeating times 10 to the minus 20th joules. The reason that I'm writing it out this way is we can use our dimensional analysis to make sure that our units are working out the way that we think that they should. Our joules will cancel out. Our seconds will cancel out, giving us meters, and meters is a unit of distance, which agrees with our wavelength, right? Wavelength is a distance, and so we should end up with units of distance. So if you plug that into your calculator, you will get 7.45549 times 10 to the minus 6th meters. To work out our significant figures, our Rydberg constant here that we were using has 3 significant figures. Our principal quantum numbers, n equaling 6 and 5, these are integers, and so they have an infinite number of decimal places. They don't get counted when we're looking to try to determine significant figures. So what this tells us is that our energy of the electron should have 3 significant figures. Then when we do our calculation for our wavelength, Planck's constant has 4, speed of light has 4, and this value here for our energy had 3. So our n value should have 3 significant figures. So this would be equal to 7.46 times 10 to the minus 6th meters. If we convert this into nanometers, that would be 7,400 and 60 nanometers, which would be in the IR range, which agrees with our experimental observation that transitions between 6 and 5, which should give us very long wavelengths and very low frequencies.